Hello and welcome back to the final stretch of LINX117. We've got three sessions left to go now. And the first one we've got Andy van Vloten Martin, who's from Blaze Manufacturing Systems. Now this is a talk that I saw at a Host in Scotland event back in September, and there were some interesting little case studies in there. So we invited Andy along to speak to the LINX members, so I think this will be an interesting talk. So if I can invite Andy up, please.
Good afternoon, ladies and gentlemen. Yeah, I think I could just about read the screens. So I've got the afternoon shift. I've got the post-lunch snooze moment. So yeah, reduced numbers as well. We'll whistle through some slides. I work for Blaze Manufacturing Solutions. We do fire suppression and fire detection systems. And we're going to go through a whistle-stop tour of things to consider in detecting and protecting data centres. So we've got an overview of the presentation, a little background who Blaze are, going through the various steps, considering what you need to take into account, look at the various options, fire suppression systems, and talk about some of the things you need to take into account when you're planning, when you're looking to protect different enclosures. Who is Blaze? It's a family. It started off as a family-run business, 2006. A lot of colleagues, ex-Tyco, been around the industry quite a long time. We work in all different applications, offshore, onshore. We look at the front end of system design, look at front end building design, look at protecting existing structure, look at protecting or changing existing systems to suit as changes in the industry come about. So the first step that we need to consider, I'm sorry, I'm actually quite struggling. Could you make the screen bigger, please? I've turned 50 this year, and I am struggling to see the screen. That's super. Thank you very much. So the first step that... no, you've made that really small there. Yeah. So I could perhaps half and half now. That's better. Thank you. So what do we need to take into account when we're looking at the protecting of different rooms and understanding the process of fires and how they start, how they spread, and how to put them out? What requires protection? There is a philosophy in different industries not to bother. So, for example, wind turbines. There are so many wind turbines in the field. It's considered don't bother protecting the individual turbines. Just protect the transformer platform itself. If the turbine goes on fire, leave it to go out, because the cost of protecting each of the individual turbines is significantly more than the cost of losing one of the turbines. Same could be argued about certain areas within the data center, but that's on a risk assessment. That's a case by case. What do you need to consider? Look at the criticality of each of the individual cabinets. Are you protecting the whole of you're protecting structure, you're protecting the building? Is it the end of the world if a single cabinet falls out? If it is, look at cabinet protection in particular. If you're looking at preventing fire from spreading through the whole of the enclosure, look at the total flood of that enclosure itself. Response time, early detection. As soon as a fire becomes big is hard, difficult to put fires out. So the sooner you can detect a fire, even in the very early stages, before you can even smell smoke, there is equipment available on the market, Vesta, Fast, the two different makes, Honeywell, VESDA themselves, who detect fires or detect the smoke particulates before conventional smoke detectors that you would see in this sort of building could detect. Gives you an opportunity to go into the various rooms, go have a look at where the individual detecting point has located the smoke. Think about sensitivity to water. So water is plentifully available. You can deluge. This sort of room would have a sprinkler system, although I don't actually see any sprinkler heads. Okay, never mind. You could consider water mist, a small particle droplet. So rather than having a large water droplet as you would from a sprinkler installation, a microdrop is a lot smaller particulate, which takes the energy out of the fire. So it converts the water droplet itself to steam, and that suppresses the fire by taking the heat out. And then other considerations, what the national standards require to look at. So in particular, large enclosures, sensitive electronic equipment, disk drives, you more often than not looking at gas suppression systems. There's two schools of thought, or two families of agent that you could consider. The halocarbons, which are the direct substitute from halon, back in the day when before the Montreal Protocol came in, or the inert gases. So the chemical agents, the halocarbons, they look to chemically attack the fire, whereas the inert agents, they reduce the oxygen concentration, so they don't do anything about the heat. They reduce the oxygen concentration to starve the fire. The halocarbons of today are far less impacting environmentally than halon used to be. So they stay in the air, they stay in the environment a lot shorter durations, typically 5 days rather than many years for halon. They don't affect the ozone layer. So it's all considerations that need to be taken into account. Inert gases, various forms, usually from naturally occurring sources. So IG541 there, Inogen, it's a mixture of argon, nitrogen and CO2. The next one, IG100, nitrogen, 55 nitrogen, argon or CO2. CO2 is frowned upon because it kills people in the concentrations that you need. But it's cheap. Early detection. Can't have everything, can you? Early detection recommended. So, as I said on one of the previous slides there, look to put something in, be it VESDA, be it FAST, that can detect the fire way before conventional detection will sniff it out and investigate what's going on. It does mean sending people into the data center, go have a look at which cabinet or which area has been detected. But in the long run, it's better to do so. But I would never put a fire suppression system on the back of an early fire detection system because it's too early. So back to school days, looking at what you need for a fire to occur. You need the three elements, the fuel, oxygen and heat, or spark potential. And if you have these three together, you have a fire. You can break the fire by breaking the chain reaction or removing one of those parts within the fire triangle. And most of the inert agents, or all the inert agents, do away with the oxygen by substituting it with an inert gas. You could also think of it as if you've got a fire blanket, for example, you put that over a fire, you're not only cutting off the oxygen, but you're also smothering, you're taking the flame front away from the layer that's on fire. So the inert agents themselves, so we've already spoken about the mixture of different gases that you can put together to suppress a fire. Essentially, all you're doing is substituting the oxygen in the air that you're breathing and replacing it with something that doesn't burn. You have that in day-to-day, so the higher you go, the higher you get from sea level, the lower the oxygen concentration. So at 2,500 meters, you get down to 15% oxygen levels, so it's difficult to ignite something. At 4,500 meters, down to 12%. You can still burn things at 4,500 meters. 5,800, you're down to 10%, so that's around the top of Kilimanjaro. When you get to those sort of elevations, you get to that level of, or the reduced level of oxygen concentration, you then tend to get very lightheaded. You have effects that you need to take into account. So when we're designing fire protection systems, we always make sure that the oxygen concentration doesn't drop below 10%. Otherwise, if you have somebody that's knocked out during an event, they're unconscious on the floor, oxygen concentration drops below 10%, and they could asphyxiate, they could have other issues. So we have there the various mixture. We're looking at, in the normal atmosphere, 21% is oxygen, and reduced, and the CO2 level is well below 1%. And for the inerting agents, we're looking to reduce the oxygen concentration below 12%. Inogen is a funny one, the mixture of nitrogen, argon, and CO2, because we actually introduce a little bit of CO2, which gives you the effect of blowing into a paper bag, so that even though you've got a reduced oxygen concentration, by blowing into the bag or breathing in some carbon dioxide, it opens your respiratory system, so it allows you to breathe the low oxygen concentration and have lesser effects. Or it's a marketing blurb from Tyco, who brought it to the industry. During a discharge, you're going to get a lot of noise. Typically 80, 130 decibel. It's very loud, very disorientating. If you are around when a chemical agent goes off, when a halocarbon goes off, they produce a very fine mist, and it's sort of cloudy. For the other inert agents, it's colorless, but even still, it's very disruptive. Also has a big impact on hard disk drives. There was a study that Tyco Michigan Technical University undertook to look at different types of hard disk drive and the effect of noise levels on them. And it was concluded that in order to lessify or reduce the impact of damage on the hard disk drive, you needed to reduce the sound pressure level to below 110 dBz. You can also reduce the levels by having a constant flow. So what we're showing here is two different types of release. The high peak is showing a conventional orifice type system. So you have a cylinder that's got 200, 300 bar of inert agent, and it's being released through a restriction orifice, 2, 3, 4 millimeters diameter in the pipework, and that creates a massive pressure spike in the room. That also creates a lot of noise as well, because you've got a lot of gas escaping out of the nozzles in a very short space of time. So to reduce that, you can have a regulated flow, which means that you have a constant pressure at the valve, at the cylinder valve. In reality, the pressure increases and it drops, and it hunts to the set pressure of the system, and then at the end of the discharge, then it drops off down to atmospheric pressure. So the things that we need to consider when we're looking at different systems. First and foremost, early detection. If you can detect the fire before there's even a flame, before there's even the sign of smoke, far better. You can isolate the cabinet, you can investigate, whatever's going on. So if you take nothing away from this presentation, small fires or early detection is definitely better than trying to put a fire out. The early systems are 800 times more sensitive than point detection, so the regular smoke detectors that you'd have in a conventional building. So they are extremely sensitive, and that's the reason why I would never put a fire suppression system on the back of a very early warning system. Consider room integrity. What does that mean? If you've got opening doors, if you've got transits going to different rooms, if you've got false ceilings, false floors, the room that you're trying to inert, the room that you're protecting, has to remain airtight or not allow fresh air to enter into the enclosure within at least 10 minutes. So you want to have that concentration of agent that's been released in the room for at least 10 minutes. So if you've got leak paths out of the room, the oxygen concentration is going to rise, and you're probably going to get reignition. Another option is that you could positively pressurize reduce the oxygen concentration all the time in the data hall or in the enclosure being protected to under 15%. This is called a hypoxic system. It's impractical, really, for data halls to do this. Because it's a positively pressurized enclosure, and so in which case you're going to lose the agent. Other points to consider for normally occupied areas, so where personnel are. You think about exit routes, how to exit the enclosure where the fire protection system has been put in place. Look at the design concentrations. So I said about the 10%, the 12% oxygen levels. Look at handheld extinguishers. Extinguishers are good, but you can only fight small fires, so that they are ideal for occupied areas. Think about fireballs. There's a picture there of one. It's a equivalent of a dry powder extinguisher. So you roll the ball, or you position the ball somewhere above a fire. When the flame touches the ball, it explodes, setting off a cloud of powder, and suitable for all the ABC fires. Looking at unoccupied areas, you need to think about things like the ceiling voids, the floor voids. They are more often than not heavily congested. Lots of cables. They're going to get warm, difficult to get to. You're not going to see what's going on behind the tiles behind the floor. So you need to think about placement of nozzles and protecting those as well. Look at the HVAC. So you've got cooling all around the building. There's no one answer. Should you turn the HVAC off during a fire, or should you leave it on? It all depends. By circulating the airflow, you're also circulating the inert gas. You're circulating the halocarbon being released. So consequently, you're going to get the agent to all parts in the room. But you need to take that extra volume into account. It may be that for the It may be for the enclosure, you've got the HVAC within the enclosure, in which case, definitely leave it switched on. If it's outside the enclosure, as I say, you need to take that volume into account. Looking at the room itself, you've got various places that you need to consider. You've got closed areas within the room. You've got the floor voids, and up in the ceiling, you've got multiple airflows. So think about placing nozzles not only above, below, but also in the cold aisles. Otherwise, the agent wouldn't get there, and that's more likely to be where the fire is taking place. overpressure venting. So when you release all of this agent into a room, it's a lot of extra volume. So if you're not careful, you're going to blow the bloody doors off. So you need to have an overpressure vent. What does that do? When the agent goes in, overpressure occurs. The vent is already sized for the overpressure, for the strength of the room, and the vent opens, allows the excess pressure to be relieved, and then when the pressure drops back to standard again, the damper closes. Multiple different types of damper. You can have gravity, as I've just said, or electrically operated, pneumatically operated, different solutions for different applications. Afterwards, after you've had a discharge, you've got a lot of cleaning up to do, not just for the products of the fire, but if you've not selected the agents with thought in mind, you could have a lot of water damage. Dry powder. I wouldn't be releasing powder around if I was in the room. Look at the refill costs. So if you have a large area, a large volume that you're protecting, you have a large fire suppression bank cylinders, you may be better splitting it up into smaller sections, in which case you've got a smaller volume being released. It's a lot cheaper on the long term. Water mist systems use a lot less water than sprinklers. So away from the data center, away from the electronic equipment, where sprinkler is more suitable, water mist might be a better option, because the effect of cleanup and the effect of water damage is a lot less with a water mist system. And then think about your back up to running time. So by having a connected reserve means that if you have had an incident, you've got a second bank that you can easily connect, or can be a connected reserve, so that you're back up and running whilst the discharged cylinders can be replaced. That concludes my presentation. 23 minutes, that was quite good. Are there any questions?
Do we have any questions for Andy?
Okay.
No.
Thank you very much.
Was there any other case studies that that you mentioned one or two of those when we were up in Scotland?
Yes, we did. We spoke about various ones. People are stupid. People.
You see why I wanted to get it in now, didn't you?
Some people are stupid. Some people are very curious. What happens? They see a fire system. It looks all very innocuous, sitting there at high pressure, but you don't see the effect of what it can do. And they see the "don't press this button" on the wall, so they press that button on the wall. Yeah. It keeps me in business anyway. We come across different systems, different places, on heli decks, for example, offshore platforms. If you set up a heli deck system whilst there's a helicopter on the deck, that's not going to go well, is it? But it happens. There's so many.
Oh, right.
There's so many acts of stupidity. The best way of protecting or preventing it from happening is to have isolations and key locks, but you want to make them accessible to be able to set the system off in the event of. I can't think of what the case studies were that I was talked about in Edinburgh.
Yeah, but anyway, thank you, Andy. I really appreciate you coming down for that.
No problem.